Hey, what's up everybody? It is Mr. Boylan, and today we are going to explain how pH, pouvoir hydrogène, of aqueous solutions can be controlled with buffers. As always, breaking it down, we are first going to define a buffer and describe the important components of a buffer. What is a buffer? I'm buffer than you. And second, we're going to explain how a buffer works to resist changes in pH. Okay, so first, a buffer. What the heck is it? It is something that resists pH changes by neutralizing any added acid or base. Boom, definition, buffer. Okay, now what is a buffer going to contain? It will either contain significant amounts of a weak acid and its conjugate base, usually from a soluble salt containing that conjugate base ion. If you take a look at your notes, there's a thriller of a diagram there. You've got to recall that your weak acid is not going to dissociate very much into that conjugate base. And so in order to have that conjugate base in solution at any considerable concentration, we've got to supply it from some other source. Typically, it's some other soluble salt that has that same conjugate base ion. You can also have a buffer that consists of a weak base and its conjugate acid. Once again, keep in mind though, its conjugate acid is going to be supplied from some soluble salt, as a weak base is not going to dissociate and therefore its conjugate acid has to come from some other source. Again, a thriller of a picture on your notes. Okay, so now we know sort of what a buffer does. It resists changes in pH, and we know what it consists of. But how do they work? Well, basically, we apply Le Chatelier's principle to weak acid equilibrium. So as we take a look at the next couple of slides, I just want you to keep in mind the general equation for the acidic buffer composed of a weak acid and its conjugate base, provided to you on your screen. It's also really important to keep in mind as we work through these next couple of slides, the equilibrium constant that applies to that equilibrium expression. Okay, so as you take a look at your screen, we've got sort of our weak acid, and it is in equilibrium with its conjugate base and the hydronium ion. And as you notice, we're sort of encompassed, we're in the sea of water. So it's sort of set up a little bit differently there. And how a buffer works is if you add, for example, a strong base to this buffer solution, it is essentially neutralized by the weak acid molecules forming additional conjugate base. And why this is important is because it essentially leaves your hydronium ion or hydrogen ion concentration alone, sort of keeping that pH or pouvoir hydrogène, your hydrogen ion concentration, about the same. Likewise, if you were to add a strong acid or add a bunch more hydronium ion to this buffer solution, you have a bunch of conjugate base in solution to neutralize that added acid, making more neutral acid molecules. Once again, you're sort of leaving that hydronium ion concentration alone, resisting the change in pH. Now, a couple things to keep in mind. The buffer can only handle the addition of so much acid or base before it loses its buffering ability. It's called the buffering capacity, and that's essentially the amount of acid or base that you can add without causing large changes or shifts in pH. It's important to recognize that the buffer capacity increases with increasing concentrations of the buffer components. So more weak acid and conjugate base that you have, the more added acid and base they can neutralize. And secondly, the buffer capacity increases as the relative concentrations of your weak acid and your conjugate base become similar to each other. In other words, a ratio of 1 to 1. And that's important because if you have equal concentrations of the conjugate acid and conjugate base, they'll do a good job of both neutralizing strong acids when they're added and strong bases when they're added. So if you take a look at your screen, we look at this buffer situation again. We are now going to add some hydroxide, which is going to be neutralized by the weak acid molecules that are still in solution there. We form some new conjugate base ions in solution, but we essentially resist the change in pH, or we resist changing the concentration of the hydronium ion. But now let's add some more hydroxide ions. So we add enough that essentially we use up all of the original weak acid molecule. Again, we're going to make now a bunch of conjugate base, if you will. And now when we add even more base, now we're going to start using up that hydrogen ion, and we're going to have huge swings in pH, because we no longer have that weak acid molecule to sort of neutralize the incoming base. Okay, and the last thing to think about when we think about buffers, and essentially what's going on with buffers, is essentially when you add that salt that contains the conjugate base anion. And again, you're shown in your notes here, it's usually some sort of sodium salt. The anion in that sodium salt is going to be the conjugate base of whatever weak acid you're working with. So as you think about your equilibrium constant expression, when you add that salt to create your buffer solution, essentially you put a bunch of this ion, your conjugate base, in solution. It's going to react with the hydronium ion and shift your equilibrium to the left. So you're going to form even more unionized acid in solution, and therefore decrease the hydrogen ion concentration, making it less acidic or more basic. And so as you look at your notes, you're provided with a little picture to help you visualize what's going on here. If you had just the weak acid in solution, its pH, in this case acetic acid of a 0.1 molar acetic acid solution, would be a pH of 2.9. If you take a look at the sodium salt that contains that same ion as the conjugate base of our weak acid, it's a basic pH. And so when you add that sodium salt to the weak acid to make your buffer solution is going to have sort of a less acidic or more basic pH than your original acid solution would have.